All right, let's dive into a really powerful financial tool called the Geometric Gradient Series. If you work in engineering or finance, you've seen it. Costs that don't just stay flat, they grow by a percentage each year. Well, by the end of this guide, you're going to have the formulas and the method to tackle these changing cash flows with total confidence. So, have you ever run into a situation where, say, maintenance costs are jumping up by a set percentage every single year? Or maybe you're looking at a project where the revenues are actually expected to shrink at a steady rate. Yeah, that's not just simple math. It's a geometric problem. And knowing how to figure out its value today is absolutely crucial. So let's start with the basics. In this first section, we're going to get a really clear definition of what a geometric gradient is and, what makes it so different from other cash flows we run into. Okay, so a geometric gradient is just a series of payments that changes by a constant percentage from one period to the next. We call that rate of change G. And the key word there really is percentage. It's not like an arithmetic gradient, which changes by a fixed dollar amount. This one grows or shrinks proportionally, which is way more common in the real world. And this slide just lays it out perfectly, right? You've got two main flavors. On the left, a positive G means your cash flows are growing. Think of maintenance costs that just keep climbing. Then on the right, a negative G shows decay, maybe like the revenue from an old piece of equipment that's becoming obsolete. It's the same idea, just, going in opposite directions. All right, so now we know what it is. Let's get to the how. We're moving into the actual tools you're going to need to calculate the present worth of these series. And it really all boils down to two main formulas. See, the absolute key to solving these problems is understanding the relationship between two numbers. G, that's our growth rate, and I, the interest rate. You always have to ask, are they different or are they the same? Your answer tells you exactly which formula to grab. Most of the time, you'll be in the situation on the left, where G and I are not equal. But every once in a while, you get that special case on the right where they match up perfectly.
So why do we even have two different formulas? It's actually a pretty neat math trick. If you look at the denominator in that big formula on the left, you see I minus G. Well, what happens if I and G are the same number? That denominator becomes zero. And what's the first rule of math? You can't divide by zero. So that's exactly why we need that second, much simpler formula just for that specific situation.
Okay, theory's great, but let's make this stuff real. We are going to walk through a classic engineering economics problem. It's about a valve at a coal power plant, and it's going to show you exactly how to put what we've just learned into practice. Okay, so here's our setup. We've got an initial cost of $8,000. The valve's life, N, is 6 years, and at the end of that, we can sell it for a salvage value of $200. Now, here's the gradient. The maintenance starts at $1,700 in year one, but then it grows by 11% every year. That's our G. And the interest rate, our I, is 8%. Now, to find the total present cost of this whole project, we're going to follow a simple three-step game plan. First, we'll handle the hard part, finding the present worth of those growing maintenance costs. Second, we'll figure out the present worth of that future salvage value. And finally, we'll just add everything up, including that initial cost, to get our final answer. Easy enough? Okay, this is the perfect spot for you to jump in. We know G is 11% and I is 8%, so they're definitely not equal. So go ahead, hit pause on this explainer, and just try to calculate step one, the present worth of those maintenance costs, the piece of G. All right, let's see how you did. You should have plugged in a negative 1700 for A1 because it's a cost, then 0.11 for G, 0.08 for I, and 6 for N. When you run all that through the big formula for G not equal to I, you should get a present worth for that maintenance of negative $10,125. Now for the easy parts. We've got the initial cost of $8,000. That's already a present value, so we don't have to do anything to it. And then we just need to find the present value of the $200 salvage we get way out in year 6. All we have to do now is bring these values to time zero and add them all together. So let's bring it all home. We take the initial cost of negative $8,000, we add the maintenance present worth, which was negative $10,125, and then we add the present worth of the salvage value, which is a positive $126. And the grand total? The total project cost, in today's money, is negative $17,999. Doing that calculation with a calculator is awesome for understanding how it works. But in the real world, you gotta be efficient and accurate. So in this next section, let's build a reliable toolkit you can use to nail these problems every single time. I mean, just look at that formula on the screen. That is what you'd have to type into a single spreadsheet cell. Can you imagine? One wrong parenthesis, one little typo, and the whole thing is shot. There is absolutely a better, smarter way to do this. And here it is. Using a spreadsheet to break down the problem is just so much cleaner and safer. It's how the pros do it. You can see every single part laid out clearly. This basically eliminates errors, and hey, if a variable changes, like the interest rate, you can update your entire analysis in a second. And look, it all adds up to the exact same total, negative $17,999. So here it is. This is your takeaway checklist for any problem like this. 1. Lay out all your cash flows. 2. Find G and I and immediately ask, are they equal? 3. Based on that answer, pick the right formula. 4. Calculate the present worth of just the gradient part. And finally, 5. Sum that number with the present worth of everything else. If you follow these 5 steps, you literally can't go wrong. Okay, it is time to put your new skills to the test one last time and really lock in these concepts. Let's do a final challenge problem together. All right, for this final challenge, we're looking at a revenue stream from a steel plant. It starts really strong at $50 million in year 1, but then it decreases by 12% every single year for 5 years. That means our G is a negative 0.12. With an interest rate of 10%, your job is to find both the present worth and the future worth of this entire revenue stream.
This is it, your final exam. You have all the tools you need. Go ahead and pause the explainer right here and work through the calculations for both the present worth, P sub G, and the future worth, F.
So, how'd you do? If you use the formula for when G and I are different, you should have found that the present worth of that declining revenue is $152.8 million. That's the total value of all 5 years of shrinking revenue, all brought back to today's dollars. And to get the future worth? Well, that's pretty simple. We just take our present worth of $152.80 million and push it forward 5 years at our 10% interest rate. And the result? The future worth of that revenue stream at the end of year 5 is a whopping $246.08 million. And there you have it. You now have the fundamental skill to model any cash flow that grows or decays by a constant percentage. So the only question left is, what are you going to do with it? What financial projection or cost analysis or investment opportunity are you going to tackle first? The tool is all yours now. Go use it.